Now we start chapter 2. Of the book, and this is about congruences in the set of integers z and modular arithmetic. We start with the definition of congruences. Let A, B, and N be integers and a positive integer. We say that A is congruent to B modulo N. I frequently say mod N for brevity, or same thing, same sentence can be written as A 3 dashes congruent to B mod N. This is a notation for the sentence A is congruent to B modulo N. This means N divides the difference A minus B. Of course, when N does not divide the difference A minus B, we'll say that A is not congruent to B mod N. That means that N does not divide the difference, and we say that A is not congruent to B mod N, with the meaning that N does not divide the difference A minus B. With this notation, with this definition, we get a relation. So, congruence this 3 dash symbol is a relation on the set Z of integers. And the first statement about all that is something equivalent to what is written in theorem 2.1 in the book. I will reformulate that theorem simply saying that the relation on Z is an equivalence relation. I recall the meaning What does it mean? Equivalence relation. This means that the relation satisfies several requirements. It is reflexive, means A is congruent to A mod n, whatever A is. It is symmetric, which means A is congruent to B for two elements A and B of Z, two integers, mod n implies B is congruent to A mod n, whatever A and B are, as soon as A is congruent to B, B is congruent to A, and transitive. A is congruent to B mod n, and let me write it this way, B is congruent to C mod n. These two congruences imply A is congruent to C mod n. The proof that all these three requisite requirements for being an equivalence relation are satisfied is absolutely straightforward. You can do it yourself or look up in the book. That's very easy, as soon as you understand what you are doing. Thus, for every positive integer, and it's just positive, for every positive integer n, we have corresponding equivalence relation congruence modulo n on the set of integers Z. As soon as we have an equivalence relation on a set, the set is partitioned into a disjoint union of equivalence classes. Thus, Z is partitioned into a disjoint union of equivalence classes. You can think about that as some set is partitioned into a disjoint union of equivalence classes. Every two elements in the same class are in relation. Two elements in different classes are never in relation. That is something you should know in advance, and that has nothing to do with whether we deal with integers, congruences, or we just have a set and equivalence relation on the set. As soon as we have it, we'll have a partition of the set into a disjoint union of equivalence classes. In the case of integers and congruence relation, that is what theorem 2.3 and corollary 2.4 are about. I do not recommend you to follow the proof of all these facts in this specific situation. Those who do not remember have to refresh it from whatever you learned in Trait 101. Now, in the case of integers and congruent relation, we have a notation. For an integer e, we temporarily denote by A the equivalence class to which A belongs. That is, all elements in relation with A, all elements congruent to A. We call it congruence, a congruence class. Thus, we have that A in brackets is a set of integers in the first place, such that this in every integer in this class is congruent to A by the definition what congruence class is an equivalence class. All elements in relation with A. B is congruent to A mod n. What we fix n, introduce equivalence classes. This is same thing from the definition of what does it mean to be for two integers to be congruent modulo n. Their difference is divisible by n, and we can rewrite it as all integers b such that n divides the difference a minus b. Or we also can try to describe that very explicitly. What does it mean? A minus b is divisible by n. N divides a minus b means that a minus b is kn for some integer k by the definition of divisibility, which means that b is equal to a minus kn. Minus or plus here does not matter. I can write minus here. It's the same thing. K is an integer or minus k is an integer does not matter. It's a matter of notations, and it's nicer to write plus here. So these are all integers b, or even already not. B is a plus kn, so these are all integers a plus kn for all k in z, for all integers. This is a very explicit description of an equivalence class which contains A. Thus, we have a description of an equivalence class. Now, it's natural to ask, what about the set of all equivalence classes? How does it look like? Can we describe that? And the answer is yes, we can. And we do it with the help of Euclid's lemma. So now description, this is, let me write it, that this is altogether description of an equivalence class. The equivalence class which contains A. By the way, in this case, when equivalence class contains A, let me write that before going to all equivalence classes. So it contains every element of this form, and A is a representative, just to write down this word for you, of its equivalence class. Every element is a representative a plus n, a minus 17n. They are all representatives of the same equivalence class, this one, which is denoted as a in brackets. Now, let us describe all equivalence classes. Or let me speak about congruence classes. Modulo n. N is a fixed integer which is positive. If it's an integer, we ask about the set of equivalence classes. What is instrumental in this description is Euclid's lemma. Euclid's lemma allows us for any integer a, write it a, we have a equals n q plus r, where r is an integer from 0 up to n minus 1, strictly smaller than n, smaller or equal than n minus 1. It is clear that a is congruent to r modulo n. That is simply because a minus r is equal to nq, so a minus r is equal to nq, so n divides, q is an integer, and divides a minus r. We write it as a congruent to r modulo n. Thus, we have that what we see, we took now an arbitrary integer a and found that it is congruent to an integer r in this small interval up to positive, non-negative integer up to n. So we can state it as every integer is congruent mod n to an integer in the interval the interval is from 0 and minus 1. We can reformulate that in the language of congruence classes. So every congruent class, we take an integer, it belongs to some congruent class, R congruent to A means it belongs to the same congruence class as A. So every congruence class has a representative. A is a representative of its congruence class. R is also an element of the same class, another representative of the same class. Or you can say the same thing, that R belongs to this congruence class. We take an arbitrary congruence class and we can find a representative of an arbitrary congruence class in the interval. So every congruence class has a representative among these n numbers from 0 to n minus 1. It is now very convenient to choose not an arbitrary, but such an element as a representative. Moreover, integers in this interval, all of them belong to different congruence classes. So integers from this interval, this is nothing but a set of n integers, belong to different congruent classes. Different integers belong to different congruence classes. That is because all these integers are between 0 and n minus 1, so two of them cannot be congruent modulo n. Their difference cannot be divisible by n simply because it is smaller than n. Difference between any two numbers in this interval, the length of interval, the biggest possible difference is n minus 1 minus 0, which is n minus 1. So the difference between any of them is smaller than n minus 1, cannot, smaller or equal than n minus 1, smaller than n, cannot be divisible by n. So they belong to different congruence classes because their differences are smaller than n, therefore not divisible by n. Thus, what we see that every congruence class has exactly one representative in this set. So every congruence class has exactly one representative among these integers. Thus, we conclude that the set of congruence classes can be written as zero, the class whose representative is 0, 1, so further 2, and minus 1. This is a way to write the whole set of congruence classes. Every congruence class has a is among them, because every congruence class has a representative among these numbers, and this is congruence class whose representative is one of these numbers. And they are all different. So this is a full description of the set of congruence classes. In particular, there are exactly n congruence classes. Modulo n. So we pick any number, any positive integer n, and we now have a description of an arbitrary congruence class. Here it is, as a set, and a description of the set of all congruence classes, modulo n. By the way, the fact that there are exactly n congruence classes, this is corollary 2.5 in the book. We introduce a notation for this set. Z sub n, I will read it as Z mod n as the set of congruence classes modulo n. That means Z mod n is as set, this one, 0, 1, and up to n minus 1, a set of n elements. Alright? Next, in the next video, we will introduce some operations on congruence classes modulo n. Thank you for listening.